The next thing that we're going to look at is the dot product, and one of the nice things about the dot product with vectors is it allows you to calculate the angle that two vectors form together. Alright, so let me just draw a little example for that. In the xy plane, let's say I have two vectors, somewhere, like vector A and vector B. They're going to form some angle between each other, right? And sometimes it'd be nice to really know what that angle is, particularly in physics problems, things like that. In the angle, it could be really small, it could go all the way to 0, it could be really, it could be a right angle pretty much. It could open up really, really wide. And A. Right, but they're all going to have an angle between them. And also, not just in the xy plane, there's also an angle between any two vectors in 3D space. So let me illustrate that here. There we go. So if you have two vectors in xy space, they could be in some weird orientation, they could be flat, they could be in that plane, this plane, whatever. But because they're flat lines and they're straight, they're always going to exist in a plane together. All right? And because they'll always exist in a plane, they're always going to have an angle they form between each other in that plane. All right, and it doesn't matter if it's flat or vertical or anything. They always exist in a plane, and so it's well defined what it means when you ask for the angle between two vectors in 3D space. All right, so to continue on, the dot product supposedly is going to help us do this. What is the dot product? So the dot product is defined, it's A vector dot B vector. I'll write that on the component form here. So it's A vector, A1 comma A2 dot and B1 comma B2. All right, and then ends up equaling, it's A1 times B1 plus A2 times B2. That's it. And if you're doing this in matrices, another way to think of this is if you take A1, A2 transpose times B1, B2, which is the same as writing this as A1, A2 multiplying B1, B2, then you get a row times a column, you end up with this single element matrix, but it's A1, B1 plus A2, B2. All right. But anyway, so that's the computation. Take two vectors, dot them together, you get a number out, a scalar. And what's going to help us actually, why does this work? So it actually comes from the law of cosines. So let's say I have a vector here, and I think I want this one to be A. I want this one to be B. Okay, a little hard to see here, but this vector here is A minus vector B. All right, to see that, what if I had, okay, that looks like a parallelogram. If I had negative B here, all right, if I have A plus negative B, then the vector I form, that's going to be A minus B. So right, if I take this A minus B vector and I move it up here, it's the same vector. So if this vector is A and this vector is B, then A minus B is this one right here, which is the same as the one down here, it's just been shifted. All right, and so in this setup we have vector A, we have vector B, we have vector A minus B, and I want to know this angle. Well, this top piece here is a triangle, and we can use the law of cosines. So the law of cosines is going to be the length of this side squared. All right, so the length of A minus B squared, that is vector A minus vector B. That's the length, and I want the length squared, the law of cosines, is equal to the length of vector A squared plus the length of vector B squared minus 2 times the length of vector A times the length of vector B times cosine of that angle theta. Right there. And now the next thing to do is do this all out. So let's get started. So if I have vector A minus vector B, well, that's the magnitude of A1 minus B1, comma, A2 minus B2, close, there we go. All right, squared equals, so sure, why not? All right, so this, right, the magnitude of A is going to be the square root of A1 squared plus A2 squared, but then I'm squaring that, all right? Then same thing for the B. The magnitude of B squared is going to be square root of B1 squared plus B2 squared, the whole thing squared, and let me fix that 2, and we're going to leave this part alone, the minus 2 magnitude A times magnitude B times cosine of that angle that we're looking for. Okay. So now we're going to expand this part out. I'm going to skip a little step, right? Because if you square the length, it gets rid of the square root. So here I'm going to take the square of this component plus the square of this component, and just know that the square root and the square right here are going to cancel each other out. So this ends up being A1 minus B1 squared plus parentheses A2 minus B2 squared, right? And the square root and the square have canceled. Then on this side, square and the square cancel. I get A1 squared plus A2 squared plus B1 squared plus B2 squared minus 2 times the length of vector A, times the length of vector B, times cosine of that angle we're still looking for. All right, now I get to expand this part out. Okay, so I think I have enough room. Oh, so foiling out, whatever, we get A1 squared minus 2A1 B1 plus B1 squared, or 1, okay, plus A2 squared minus 2A2 B2 minus, no, plus B2 squared equals, all right, yeah, I think I did that right. Okay, equals A1 squared plus A2 squared plus B1 squared plus B2 squared, 1, 2, 1, 2 squared, minus 2 times magnitude A times magnitude B times cosine of that angle. Okay, now things are going to simplify just a tad. We actually have some common terms on both sides. Here we have an A1 squared, there's an A1 squared, so I'm going to subtract that from both sides. We have a B1 squared, we have a B1 squared, I can subtract that from both sides. We have an A2 squared and a B2 squared. Here's an A2 squared, here's a B2 squared. So what we're left with is negative 2 A1 B1 minus 2 A2 B2 equals negative 2 times the magnitude of A times the magnitude of B times cosine of that angle. And now if I get rid of the negative 2, so divide both sides by negative 2, we'll end up at A1 B1 plus A2 B2, right, dividing out the negative 2 equals magnitude of A times magnitude B times cosine of that angle. This is the dot product. This is A dot B is equal to magnitude A times magnitude B times cosine of the angle. So if I do want to know what that angle is, as cosine theta, well, cosine theta is equal to, I could take the dot product and divide by the magnitude of A and the magnitude of B. So A dot B over magnitude of A times the magnitude of B. And then you can do cosine inverse, and you're going to get a number between 0 less than or equal to theta. Let me make those a little more emphasized. 0 less than or equal to theta less than or equal to pi. All right, so if you're 0, then your vectors are right on top of each other. And then if you start increasing, you get to pi over 2, they're perpendicular. Then if you keep going, you get to pi, so they're pointing in exact opposite directions. But here we go. So this is the dot product. We derived it using law of cosines and this little parallelogram with A and B that we made. And it's a handy way to come up with the angle between two vectors. We're not going to do it in 3 dimensions, but it also works in 3 dimensions. The same property holds in 3 dimensions. And so let's get on to the next chalkboard and learn more uses for the dot product. So a few more nice applications of the dot product. So one thing it can do is it can help you tell if 2 vectors are parallel or if they're at right angles to each other. All right, so before we had A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. All right, so there's a few special cases. So one of the cases, if you have A and B form a right angle with each other, then that angle is pi over 2, and then the cosine of pi over 2 is 0. All right, so if A and B are, and it's got a few names, perpendicular, orthogonal. Sometimes you actually see this symbol, which is supposed to be a right angle. It's also, form a right angle. If A dot B equals 0, because then the cosine of that angle, the right angle, will equal 0, so A dot B will equal some number times 0. All right. You can also tell if they're going to be parallel with each other. So, pretty much the same vector, just maybe different lengths. So if you have, vector B and you have vector A are right on top of each other, then A dot B will equal magnitude of A times magnitude of B times cosine of 0. All right, I tried to make sure that it didn't look like a theta, it's a 0. But cosine of 0 is 1. So then A dot B equals magnitude A times magnitude B when they're parallel. When I'll say pointing in the same direction. It's slightly different if they're pointing opposite each other. So if I have vector B and I have vector A, and they're pointing exactly opposite to each other, then you're going to have A dot B equals magnitude A times magnitude B times cosine. In this case, the angle is pi. It's a full 180 degrees. But cosine of pi equals -1. So you'll end up with A dot B equals negative magnitude A times magnitude B. All right, and so pointing in the same direction, so this is pointing in opposite directions. In opposite directions. So that's a little useful for angles. You can tell if things are orthogonal or not. A lot of times you'll actually use this to create another vector that is orthogonal to one you already have. Like if I already have vector, this purple one, and I want to make a vector in 2D space, and I want to make a vector that's orthogonal to it, then I can actually solve for, okay, well, if I have, blank numbers, let's say this vector is, 3, 2, and I want to make a vector that's orthogonal to it. All right, then what I can do is I can say, well, okay, let's call this vector A, whatever. All right. So if I have A1, comma A2, dot the vector I have, 3, 2, I want that to equal 0. Well, if that's the case, then I want 3 times A1 plus 2 times A2 equal to 0. So one option for that is I could have A1 equals, let's just say -2, and A2 is equal to +3, right? Because then I'll have 3 times -2 plus 2 times +3. That'll cancel out. And then this one, yeah, it looks like I've drawn it correctly, probably. Yeah. So if I saturate here, y and x, then plausible vector for this is -2, 3. But keep in mind, it's not unique. I could have made a vector that was longer. I also could have made a vector that was in the opposite direction. And so it gives you a way, which will be useful in the future, to actually, if you have a vector already, you can create another vector that's orthogonal to it. So another use of dot product is the projection. It's called projections. Let me just draw a picture of it. So let's say I have, vector A, and I have vector B, and I want to project A onto B. So what that means is, let's pretend A, I have this dashed line to the whole thing, and I want to know if I were to take the vector B and bring it essentially directly down at a right angle onto that direction of vector A, how long will that be? And also, what is a vector representing that? So that's called the projection. You're projecting B onto A. So project B onto A. All right. So how do you do it? Well, all right, so we have a right triangle here, so we can use that as a hint. And so if I wanted to know what the length of B is going to be, right, on this piece, right, so I have here, if this is the angle I have, right, I'm going to use dot product, so I'm going to use an angle. All right, remember the dot product, so I've got A dot B equals magnitude A times magnitude B times cosine of an angle. All right, so cosine, that is adjacent over hypotenuse. Of this right triangle, if I'm using B, right? So B is the hypotenuse, and then this is going to be the adjacent side, this length. I should say the length of B is the hypotenuse, and the length of this is going to be the adjacent side. Right, so then if I were to take cosine of theta and multiply it by the magnitude of B, well, that would be like taking the adjacent over hypotenuse and then multiplying by the hypotenuse, because that is the magnitude of B. Let me make that B a little more B looking. All right, so that would just give you the adjacent, which is the side length we want. We wanted this length. All right, and let me just put that in this picture. All right. So then, okay, well, we're almost there with A dot B, right? Because A dot B, I've got the magnitude of B times cosine theta, but I got this extra A. Well, what if we just divide by magnitude of A on both sides? So if we say that we're going to have A dot B, and I'm going to make that B nicer again. I'm going to multiply that by 1 over magnitude A. Right, if I multiply, so that's on the left, multiply by 1 over magnitude A, multiply on the right by 1 over magnitude A, the magnitude A goes away, it becomes a 1, cancels out, and ends up with just magnitude B times cosine theta. All right, and then to make this a little prettier, what we typically do is we say vector A over magnitude A, and then that thing, it's still a vector, so I have a vector A and I'm multiplying by a scalar. My scalar is 1 over magnitude A, and I'm dot product that with B. And that's going to equal magnitude B times the cosine of theta. And so that's the projection. And another way, though, to write that, it's the scalar projection of B onto A. So scalar meaning we just got the length. And one other thing to note here, if we take a vector and divide it by itself, this is called a unit vector. Because its length is now 1. If I took the magnitude, the whole magnitude of this whole thing, so if I take magnitude vector A divided by magnitude vector A, well, the magnitude of a scalar is itself, so on the bottom we just get magnitude A, but on the top, the magnitude of A is, right, magnitude A equals 1. So the length of a unit vector, units meaning 1, the length of a unit vector is 1. All right, so we take the unit vector in the direction of A, dot product with B, that's going to equal B times cosine theta, which is equal to the scalar projection of B onto A. All right, so that's the scalar projections. You want to know the length of B onto A, kind of how much of B is pointing in the A direction. And there's another one, so you could also have the vector projection. Writing's a little bad there. Of B onto A. So that one, instead of getting a scalar, we want to get actually the vector. So from here all the way to here. All right, so if I draw a little picture for that. Oh, sorry, A. And I have my dashed line, right triangle, then this will be the projection of B onto A. That vector right there in the direction of A. So in order to get that, what we actually do is we have the length of the projection, the scalar length, right? So we know how long this is. And if we want a vector in the direction of A that has this length, then we can take a unit vector in that direction times the length. So it ends up being, so let me get here. So if I take A over magnitude A, dot product that with B, so that gets me this length here, right? And then I'm just going to multiply that as a scalar to the vector B. Sorry, vector, excuse me, vector A over magnitude A. All right, so what that does is this is the length that if I project B onto A, so I've got the adjacent side length here, and then if I multiply it by vector A over magnitude A, the unit vector in that direction, then we're going to end up at exactly that length, because I take a vector of length 1, I multiply it by the adjacent side length. Now I have a vector in the direction of A with the adjacent side length. All right. So you can use dot product for other things, but those are some of the key uses and they show up quite a bit.